Hey, all right. So we're talking about position time and velocity time graphs. Okay, so here I've got some sample position time graphs, and in many cases, you're going to want to interpret the motion. Okay, so here we've got apparently some object that has a position of, it looks like 1, 2, 3, assuming each of these are 1 meter, right? So 3 meters. And then a little bit later on, it has a position of 0 meters. And then it has a position of, it looks like -2 meters. Okay. And so it looks to me like it's, and then this is north, right? So if I want to interpret this, it appears that I was at some position north, and then I was at some position a little less north, and less north, and less north, and so forth. So I appear to be going south. And not only that, I'm moving each individual second that passes here. I'm moving the same distance every time, the same change in position. So it appears to be a very constant motion eh, in the south. So if you were to describe the object's motion, which is the objective of this question here, you are moving in a constant velocity south. Okay? And that's what your straight lines are. Okay? If you're going up like this, you would be moving in a constant velocity north. Okay? If you have a horizontal position graph, you're just not moving. You have a velocity of 0, right? So those are some basic ones. But then we've got some curvy ones. How do you deal with the curvy ones? Well, it looks to me, what I tend to do is kind of break this up into, let me get out a pen here and start looking at this with maybe some pink. It's nice. I kind of say, all right, well, here's this 1 second, and I've moved this far. And then in the next second, I've moved only this far. And then in the next second, this far. And in the next second, this far. And the next second, this far. And then the next second, this far. So if you look closely here, each second, my total motion in the up direction, this is moving up, seems to be less and less and less and less. So over the course of 1, 2, 3, 4, 5, 6 seconds, I appear to be moving up quickly, a lot of upward motion in the first second, less upward motion in the second, and this trend continues. So if you were to sort of describe this motion in a single phrase, I would say we're definitely still moving up because I have a position of 1, then later a position of 2, 3, 4, until finally I have a position of, was this 1, 2, 3, 4, 5.5-ish up. That's my final position. So I'm definitely moving up, but I'm moving up with less and less sort of, magnitude. So basically, I would say I'm moving up while slowing down. Okay. You could say that I'm decelerating while moving upwards. I kind of just like to use the colloquialisms, like the standard English that you would use on a day-to-day, on the street. So I'm moving up while slowing down. Okay. Now let's analyze this one here. Here I'm moving, it appears down. Oh, but I don't want to use the word down because look, this one is clearly, it's indicated as being west. So what does that mean? That direction is west. So because this is west, that means this is west, which basically means that direction is east. So I appear to be moving east in this situation. And now let's again take a look at our second to second motion. So here in the first second, oh wow, I moved east quite a bit, right? And then in my second, I moved east quite a bit less. And in my third second, I moved east again a little bit less, and so forth until finally I'm practically not even moving east anymore. It appears that I've actually come to a stop at the end here. So it looks like, boom, I've hit a sort of stop. So what I'm doing here is I'm moving east while slowing down, okay? And then later you could even say coming to a stop. I could say decelerating east, okay? I could do any type of that situation is what you want to be looking at. All right. So you're going to want to be ready for, curvy upwards, curvy downward type situations. Okay. All right. So one of the, another common question for students at this level of physics would be to take a graph like this, position versus time, and do some conversion so that you can start to actually convert it into a velocity time graph. Okay. And so recall, as we recall, our velocity is equal to the change in position over the change in time. And so what you want to do in a situation like this is you want to start to say, all right, look, I've got three very distinct motions here. This is a constant sort of motion in the upward direction. I'm moving the same amount every second for half a second. Oh no, these are hours actually. So this is a half of an hour. It's a half of an hour. So for a half hour, I'm just moving constantly upward. Okay. So what I'm going to do is I'm going to sort of label this just to keep my thoughts straight. I'm just going to say, well, this is section A, this is section B, and this is section C, because as you can clearly see, each one of these sections are, very distinct motions, completely different motions. So let's just focus on section A for the time being. And if I want to figure out the velocity, basically I'm going to say, well, the velocity is the change in position. So the change in position is 15 kilometers west. Okay. And my change in time is a half of an hour. So I could go, since I'm doing kilometers, I could do minutes or I could do seconds. But, if you're doing kilometers and hours, that's a pretty acceptable rate of velocity to put a final answer in. And so I would go ahead and just leave this. I wouldn't even convert anything to meters or seconds. I'm going to leave this as a half of a hour. Okay. And so 15 divided by a half, remember if I divide something by a fraction, it becomes bigger, is 30. And that's 30 kilometers per hour. And I'm going to go ahead and keep the west designation on that. Okay. That's for part A. Okay. Now here for part B, if I want to do, and I can even put little subscripts here. This is A. My velocity in the B section is going to be, let's see, my change in position. Oh, well, look at this. My change in position is, well, nothing actually, because I'm at position 15 at the beginning here, and I'm at position 15 at the end. And so my change in position is actually 0 kilometers over the half hour that it takes, but it doesn't matter because 0 kilometers per hour is my final velocity there. And this is 0 kilometers per half hour. Well, it's just, 0 divided by anything is just 0. So there we go. And since it is 0, there's no reason to put a direction on there because, well, you didn't go anywhere. So let's see. Part C. Or not part C, but like, section motion style C. All right, so in here, I'm going to go ahead and do my same formula. My velocity for motion style C is change in position. So for this one, I'm going to designate this one position initial, and I'm going to designate this one position final. So remember, it's final position minus initial position is equivalent to change in position, and then divided by my time. So here my time appears to be 1 hour. So I'm going to do with 1 hour. Okay. And so my final position is actually 0. So my final position is 0 right here. And my initial position is 15. Oh, that was funny. I got like a crazy thing happening there. Okay, there we go. My initial position is 15, and my final position is 0. So I'm going to write 0 kilometers minus 15 kilometers west. 15 kilometers west. Okay? And all of this requires 1 hour to complete. So I'm going to do, my final answer is negative 15 kilometers west per hour. But a negative west is actually east. And so it's 15 kilometers east per hour. I guess I should have written it. I should have said it differently. I should have said 15 kilometers per hour east. That's the velocity in part C. Okay? Well, that's all fine and dandy, except that we didn't make the actual graph yet. So let's go ahead and make the graph, because that's the actual question. So oftentimes what I do is when I make these graphs is over here off to the side, I decide my 3 or 4 different styles of motion. I figure out the precise velocities during each one of those. And then down here below the graph, I'll make a new velocity time graph, okay? And I do with that so that I can correspond my times very nicely. So I just keep the same scale for my times here. And so that way I can break this up. So this is going to be section A, right? Well, section A has a velocity of 30 kilometers per hour west, okay? So over here, I want to do velocity. I want to label my axis as velocity, and that's going to be kilometers per hour, because that's what I've chosen. And west is my designation. And so up here, I'm going to write 30. And I end up having a full-on velocity of 30 for the entire half hour. So I have a constant velocity. Why is it constant? Because remember, this line is straight, not curved. This is a line, not a curve. So this indicates the fact that I have a constant velocity west at 30. So if you look closely here, this graph tells the viewer that for this entire half hour, I just got to put a half hour here, I have a velocity of 30. Now I have a velocity of 0 for another half hour. So I'll put this, okay, and I'll again correspond that to the 1 hour mark. Notice these guys are right above each other, okay? And now over here, I've got another velocity that lasts for, to the 2 hour mark, 2 hours. And that velocity happens to be 15. And it is again a constant velocity of 15, like this. So here's my final graph. I'm moving 30 meters per second, 30 kilometers per hour for a half hour. Then I'm doing nothing for a half hour. Then I'm moving 15 kilometers per hour in the east direction. So I can put a negative here, actually. It's a bit, well, Since this says west here, I would probably put a negative 15, right? Because my designation is west, which, as we know, negative 15 west is 15 east. Okay, so that's that. All right. Now, one thing to note is these little kinks, these are called kinks mathematically. When I have a function that takes a very sharp turn like this, it's called a piecewise function, and these would be called kinks. And so this is actually physically impossible to, you know, come to such an abrupt stop like that. This is more of a little bit of a curve. But for the purposes of, just education and doing examples, questions to interpret these graphs, textbooks will often give you position time graphs with these sort of really sharp delineations between the two styles of motion. And so, how do you interpret that on the velocity time graph? What you do is you just jump straight down to the next appropriate velocity. So, effectively, even though this is not necessarily exactly what's happening, in this person is moving or is not moving, and then at the exact some moment later, he's all of a sudden moving at negative 15, right? Which implies that during this jump, you would have an infinite acceleration from 0 all the way up to negative 15, which we all know is not physically impossible. But again, these are just graphs for educational purposes so that we as teachers can kind of see that you guys are able to sort of take the position time graph and convert it into a velocity time graph. And if you look closely here, effectively all you're doing is figuring out the slopes of these lines. Because as we know, the change in position is a change in the y sort of characteristics of this graph. The change in time is the change in the x. And if you remember from math class, change in y over change in x is effectively the slope, right? So if you look at this has a slope of 30, which is the velocity. This has a slope of 0, which is the velocity here of 0. And this section here has a slope of negative 15. Okay, so remember that for later when we, take this idea of a change in position. Yeah, is a slope. Okay, let's see what else we have here. Oh, hey, a lot of textbooks will ask you to start. We're going to start talking about instantaneous and average velocities. Okay, so here's another position time graph. And the question would be to describe this motion. Okay. And so, we're going to describe it. I'll just do a quick description of this. This appears to be moving forward here, and it appears to be moving faster and faster because I have a small amount of forward progress in the first second. Then I have a little bit more forward progress in the second second. And then in the third second, even more, in the fourth second, even more, the fifth, and so forth, such that by the last second, my forward progress is quite dramatic, right? I'm moving almost a full, what is this? This is 50 meters, 65. I'm almost moving a full 15 meters in 1 second here. So this is some pretty impressive speed at the end. And this is some pretty slow speed in the beginning. Here it takes me a second to move almost no distance at all. So I appear to be moving forward. You're just going to take the words straight off the graph. Forward, and I'm speeding up forward. Okay, so if I want to go ahead and do that, I'll just write speeding up forward. Okay, and you can just use an F in a bracket to designate forward there. Calculate the instantaneous velocity at t equals, I think this should be an equals sign. Oops, I had some copy paste crisis there. Calculate the instantaneous velocity at t equals 3 seconds. Okay, well, where's 3? Here it is. Here's 3 seconds. And, well, shoot, what's my velocity? Well, remember from the previous example, we said that velocity is equal to slope of the line, okay? Well, here, my line is like pretty curvy. So what is the slope? So if you recall, what we're going to do here is you're going to get out a ruler. You can't see this. I actually am placing a ruler on my screen. And I'm anchoring the ruler here at 3 seconds. And I'm attempting to duplicate the slope of the line. And I'm going to go ahead and extend it out in both directions. So what I'm effectively doing is making a tangent line. So this pink line represents the slope or the instantaneous velocity where at t equals 3 seconds, because there's 3 right there. And now the slope of this tangent line is going to effectively estimate the instantaneous velocity. So how do I find this slope? Well, I'm going to have to choose 2 dots on this line. Well, there's one. And so I'll go ahead and write down their coordinates. The coordinates of this one is 7 for the x-coordinate and 30 for the y-coordinate. And the units are 7 seconds and 30 meters. Okay. Now, I got to find another dot on here that's pretty good. Is this a pretty good dot? It doesn't look amazing. Maybe I can use this dot. Does this go right? Let's assume that this goes right here at 1.5 seconds. So this dot here, its x-coordinate is 1.5 for the time, and my position here is 0 meters. So now if I figure out the slope of this line, this pink line, remember the slope of a line is just the change in y over the change in x, or the velocity is the change in y, or the change in position, over the change in time. And this is at 3 seconds. And so notice I'm not even using 3. I'm just using some 2 random points that are on the tangent line. And where did the tangent line come from? It originated from attempting to duplicate the slope at 3. Okay? Well, I probably could have done a better job there, but I tried the best I can. So one thing to remember is everybody in the room who does this, they're all going to get slightly different answers, because the tilt of this tangent line that you hand draw might be a little off from the people who do this next to you. So you have to just be careful to not get, too worried. Anyway, so how do I find a slope? Well, it's the change in y, or 30 minus 0, so 30 minus 0, over the change in x, or 7 minus 1.5, 1.5. And notice the units here. 30 meters minus 0 meters gives me 30 meters. And 7 seconds minus 1.5 seconds gives me 5.5 seconds. Okay. And so yeah, that's my my instantaneous, right, velocity. Okay. And so that's what we're going to be looking at. And that comes from a tangent line. Now we have to determine the average velocity as well. The average velocity between 3 and 6. Okay, so now they're actually giving me two full-on lines. There are two full points. They're telling me you have to focus on 3 and you have to focus on 6. So I'll do this in a different color. Here's 3 and here's 6. So I'm going to go ahead and get these 2 points here. Well, my x-coordinates or my time coordinates are 3 and 6. So those are given. So now I'm going to have to sort of figure out what my position is at 3. You know what I might do? I might cancel out this line so that I can see a bit better. And then I'm going to cancel out that dot. See, yeah. So look at that. So right at 3 here, it looks like my position is maybe like 9 meters, because this is 20 meters. This is 10. So I'm going to go with 9 meters. 9 meters. Oh, I had the eraser on. Let's do 9 meters. Okay. Now at 6, now I am going to erase this dot at 6. So at 6 here, it looks to be my position is, I don't know, 36. I'm just going to go with 36. Again, do the best you can on these ones. And so now my average velocity is my final position, which is 36, position final, minus position initial, which is 9. So it's going to be 36 minus 9, and those are both in meters. And my final, my change in time is my final time minus my initial time, or 6 seconds minus 3 seconds. I wasn't putting units in here, but maybe I should, but whatever. What's 36 divided by 9? 36 divided by 9 is, divided by, that's minus, is 27. Is that right? And then over 3. Oh, did we just get a 3 meters per second as an answer? That's pretty nice. 3 meters per second. Okay. No, that's not right. That's 9. That's 9. Okay. And this one up here is like 5.5-ish or something like that, meters per second. Okay, and that's a 9. It looks like a 1 or a 7. Okay, so there we go. So again, this is a little bit of a discussion on how do we kind of analyze average velocities versus instantaneous velocities. So instantaneous velocities, they both require the slope formula, but the instantaneous velocity requires a tangent line to be drawn, whereas the average velocity, I'm just going to use the 2 points given. Use the 2 given points. All right. What points are you talking about? Well, I have to give you some times. So here I've given you 3 and 6. So you have to use those times. And I think that's all we've got for these position and time graphs. There's some various skills that you're going to want to, get yourself caught up on. Okay.